My name is János Karsai, working at the University of Szeged. I'm a mathematician, and we have been working with Mathematica for more than 20 years. And my current talk was about cellular automata modeling of metapopulation systems. And this is a very nice topic because we can investigate what we can investigate. The competition of different species, the spread of epidemiological processes, that's everything. So that's about, we did a lot of experiments, interactive experiments with my PhD students and co-authors who are very active in continuing my work. Unfortunately, it's very difficult to compete with the official work from speakers, but I try to do my best. So my name is János Karsai, and the talk is a joint work with my PhD students or ex-PhD students. The main co-author is sitting here, so if you have questions about the biological background, please go to Eva, and she will explain a lot of things about you. So I will speak about our investigations of cellular automata models of competition in metapopulations in Mathematica. So there are several words which may be unfamiliar for you. So metapopulations are such populations which are not individual based, but the territory occupied by the species is investigated. So that's what we are doing. And actually, the technical tools are quite easy to consider in Mathematica. I don't think you are interested in the abstract, so, but it is here then. Now, let's consider some introductory examples. That's quite simple. If you would like to investigate the moving average, then it's quite easy. We have to use some kind of rotating of the list, and that's quite easy to do. But the formula is there, and we can see that in the next step, the value of the process at some position is calculated from the value at the same position and the values of the neighboring position. So that's the main point of that. So that's what we can see here. And now the next one is exactly the same, but that's the heat transfer. That's a repeated nested convolution, and then we can also have a look at this kind. So this is also very easy to see. Okay. Again, the temperature at the points is calculated from the temperature. From the given point and from the temperature of the neighboring points. And actually, the space is linear here and discretized. So that's what we do. And then let's go a little bit further. And now let's consider a very simple cellular automaton that's called the Parity rule. I learned it from Eva, and I really like it. So for example, if I have a question, if I have one glass of beer in Germany, this is a current question, I would like to have more. How can I duplicate the glasses? So it's quite easy. I have to use the Parity rule cellular automaton. It's quite easy. Each self can have state 0 or 1, and that if I want to calculate the value at the next step, I add the values of the neighboring cells modulo 2. Okay, the cell itself is neighbor of itself. So now that's the rule, and then, of course, if this is the initial value, then we can have more glasses. That's it. Okay, so yeah, now. Here we have 5 glasses, and then at the end we have even more. Okay? So this is a very simple cellular automaton. And then after that, there is a very simple problem. It can be given as a task to high school students. The problem is I would like to grass or yard, and I can buy clay sods on the garden shop, and I don't have so much money. I would like to grass or yard with minimal investment. So now the self space is a
is a square with distance, and the neighborhood is the so-called Neumann neighborhood. We have north, east, south, west, and then we can do investigations. Now, in this situation, an empty square is grasped only if there are at least two neighboring grasped squares. Okay? So in that situation, we can see the development of the system. So we can see that in this case, I have to buy at least 10 clay sots if I have a 10 by 10 yard, okay? I can do something similar, but if just one neighbor is needed, it doesn't matter because it's quite fast. So this is very effective. But the problem is that in the yard there are dogs which can remove the grass or anything, so that's the probability of the effectivity of the grassing and that the extinction we can introduce. So how to do it? So now and in addition, in the theoretical biology, in metapopulations, we introduce different kind of neighborhood systems. Actually, the Neumann-Amurian and other cell systems are also used, and the boundaries can be also different. We can take into account the border, but we can use a torus-like, a toroid-like system as well. With the toroids, it's quite easy to work with. Okay, and then we can work with stochastic grassing, actually, how the empty cells are grasped, they can be grasped or not. Okay, there is a probability for that, and this probability mainly depends on the number of the grasped neighborhoods. So that's a very important point. And actually, after that, we have to introduce the extinction. There is a probability of becoming extinct or staying occupied by the given species. So that's what we can consider. Okay? And then, for this situation, we can also do some different simulations. Now I don't want to run because I have no time. At home, if you receive the notebook, you can change the parameters. You can see that the different behaviors are different in the case of Neumann and Amurian neighborhood. And the system is, the development is also different if I change from the plane to the torus. That was quite fast. So you can see that that's it. And actually, these are those experimental studies which cannot be proved quite easily by mathematical tools. So that's not theoretical. This is called sometimes experimental mathematics. And now, the next problem is more rather scientific, not just introduction. Okay, I had some time. Now, how can we investigate the spatiotemporal behavior of the logistic growth? The logistic growth is well known for everybody. This is a baby example at the first calculus and then differential equation courses. Now, there are occupied cells and empty cells, and then the occupied cells become empty, and the empty cells can be occupied by the species, so that's quite easy. And the classical Leibniz model is quite easy to see that the occupation, the colonization is described by the logistic part of the equation, and the other one is the normal extinction, that's the normal stuff. And here P denotes the proportion of the occupied patches in the space. And so this is quite easy to see, so now there is nothing new in it. But now the question is how to create the analogous cellular automaton model. Here we consider a square cell system with toroid borders, and we use both the Neumann and Amurian neighborhood systems, and the occupation is considered just 1 and 0, occupied or not. So, okay, that's it. And we define the probabilities of the colonization and the probabilities of the extinction as well. Oh, in the other order. Sorry. And those probabilities are defined using a very simple way. And here, the natural analogy of in this system is quite easy. The extinction probability is constant, but the colonization probability is a probability function depending on the number of neighbors. That's what we consider. So that was quite easy. And then this is a simple stuff when we consider a linear colonization function. So if we have double of the neighbors, the probability is the double. So that was the original investigation. And if we consider some simulations, this is quite easy to see. And what is quite strange and not strange, it's interesting that the mean field model, the Leibniz model, cannot work sometimes because if we use different initial configurations, the behavior, the development of the system can be different. And that's why we investigate the cellular automata models, because the explicit spatial behavior can be completely different from the general global mean field behavior. Okay? So now the question is, total extinction or survival happens. We can compare the behavior of the cellular automata and the mean field model, and the extinction, depending on the parameter, depends on this blue line in the mean field, and we can see that the cellular automata model shows a different behavior. That's because of the discrete nature. Okay? We just here we just reproduce the experiments of Beata Oborny from the Eötvös University in Budapest in this situation. Okay? And then we can consider many different kind of colonization and extinction functions, and we played a lot during the last many years with them. So for example, we can consider constant probabilities, some kind of logistic behavior probabilities, logistic with threshold, or we can observe that there are interspecific competitions where the species itself restricts the colonization. Because if there are too many, they eat each other or they compete with themselves. Okay? Great. So that's what we can consider. And then I would like to show you a general situation which shows the problem, the nature of the problem, even with one species. So you can see now that I can set manually the probabilities by myself. In this case, you can see that using the random initial configuration, the development is quite constant, but in the block, the species dies out. So that's the problem. And now, if I modify a little bit the survival probability, then we see, I hope it works, I modify a little bit better. Yeah, come on. Okay, in both situations, the species can survive. Okay? So just a tiny modification. This is the threshold where the phase transition happens. That's very critical. So that's why the experimental study is important, because the behavior here is completely nonlinear, strongly nonlinear. Okay, so now in the next, I'd like to consider the generalized systems for competition of two different species. Okay, here I just show you the general mean field model for the competition for the territory. In that case, both of species can colonize blank and empty patches, but they can allow to over-colonize the patches occupied by the other. So that makes the situation more complicated, and even this very simple differential equation model can present very, very interesting global dynamics. Okay? The theoretical results are shown here, and now this is just an example. On our website you can play with it, or you can also play with this notebook. That's quite interesting that the coexistence is not global asymptotical stable. This is unstable. Okay? Depending on the initial value, one or the other, the species will die out. So that's quite a problematic situation, and in the practice we would like to avoid it. Now, I have to jump because I have to finish very soon. Now, there are very interesting situations when we would like to consider now the cellular automata models, that there are invasive species. Okay? For those, there are host species. There's the original population that modifies everything slowly. Originally, this is stable. Okay? The aggressive species colonizes very fast, and it can extinct very quickly or slowly, it depends. Okay? So now this situation, this system is analogous to the well-known SIR model in epidemiology, so that's why we also investigate this system. Actually, we know well the classical mean field model for the SIR model, but we see that the cellular automaton model shows very different behavior. That's what I'd like to show. Actually, the dependence on the parameters for the extinction of the host population depends, is shown on this figure. We can see this is linear from those initial values. That fits the theoretical studies. But for the stochastic cellular automaton, we can define those transition probabilities, and we would like to investigate, actually, instead of considering the theoretical values, some development, some cases of the development. Actually, first I would like to show you how the extinction happens. So we can see that this critical line is not straight line, as we saw in the mean field model. That's why nonlinear. Actually, we didn't find a theoretical reason for that, and actually the phase transition happens here, where there the standard deviation is very huge, and the extinct values are here. And now I would like to show you the development in those situations, placing in this at these parameter settings. So that's, you can see here. I hope it works. Okay. I don't think I have to say a word to those simulations. Okay. And there is another case. Actually, the same. You can see the mean field curves for those. The green is the host species. The red one is the aggressive species, and the black shows the extinct patches on the space. So that's what we can have. And now, why we did it, we wanted to find a better mean field model. I don't think this is the best one, but this is a little bit better than the original one. Okay, so you can see that there are some nonlinear terms in the differential equation, and then we try to fit the nonlinear model to the cellular automaton model, and we can see that somehow the curvatures are similar, but that's really not the same. Okay, so that's what we have. And now finally, I'd like to show you an example of a very aggressive parasite that's called Cuscuta. In Hungarian, the name is Aranka. That's a beautiful woman name. I don't know how such a bad parasite can have this beautiful name. Actually, when we investigated, the effect was done under very short time. Under 2-3 weeks, the complete host population can be killed by this parasite. So actually, that's what we have. And as far as I know, in Sweden, this Cuscuta is under protection because this is parasite only in warmer geographic regions. In Sweden, this is protected. Okay, so now let's go to south, and now this is a photo, and now this is a digitalized version. We tried to localize the patches, and then we created the initial patches, and then we tried to do simulation, and we found that the behavior was quite good, and the fitting to the original situation was quite good. And actually, these points show here the proportion of the occupied patches taken by, calculated by photos. My PhD student every day went to the field to take photos, and that's what we did. And we saw that the fitting is quite good. And what is interesting that there are black parts. That is because Cuscuta didn't like those plants. That's why it didn't go there. Okay? And we found those patches from the last images after 3 weeks. So that's what we could find. So these patches are taken by experiment. And that is another example for the same situation. So that was the simulation, and that fits quite well to the experimental part. And there are even more aggressive situations, and I will finish. How much time I have? Just 5? Great, enough? Okay. So now in this situation, the colonization of the host by parasites shows this curve. These are the colonization probabilities depending on the parasite neighbors of the host. And now the extinction of the parasite is very interesting. Okay, if there is no host, the parasite dies. That's true. Okay, but until there is any host neighbor, the parasite doesn't die. And after that, they eat each other, and if there is nothing to eat, they die. So this shows the probability depending on the parasite neighbors of the parasite cells. Okay? And if we consider this situation, we can see that the host cells have no chance to survive if they need this case, if this parasite, if the saturation is less than 100, of course, they have some chance. But at 50%, they don't have so much. Okay, under 40, they can survive. Actually, these are the so-called percolation limits. So there are several directions to improve and to continue or research in ecology mathematically. So we have to deal with the percolation, and we are interested in the behavior of the borders of the patches. Actually, that's also interesting. We found some fractal-like behavior and so on, and we also investigate different kind of aggressivity techniques of the parasites, and we try to find real corresponding species for that. And I guess that's enough for me. So thank you very much for your attention.